Okay, so now on to drivers for the definition of the quantum compression scheme. Basically, it's just literally the same of what we've made earlier, but just formally what it is. So let's like n being into 0 to n, alpha being strictly equal to 0, and delta being to 0, and have our encoding stuff, where we have which goes to x or n, to a, to the c, to alpha n, where alpha is the rest of compression, and the decoding, it's just the other sense to really get back to what we wanted first. So that's an alpha. Is it go to LA 0n? Yeah, this is an n alpha delta compression scheme for the source row A. If the encoding minus the decoding just is less from or equal to 0, and we put the 1 before, just to normalize about it. Because otherwise it will be not between 0 and 1, and we'll have a probability not between 0 and 1. That's not fair. So yeah, that just it's where this is just any purification of row A, as we see with the bell pairs, the psi plus explaining the last video why it can work not only for orthogonal but also for any purification. It's a weird one because it's necessary anyway to conserve quantum correlation as they're implied. And yeah. So it depends on area on not only specific decomposition. So yeah, so that's it. So maybe we can say still that the alpha defined here, like as I said, the rate of compression. It's like the size of the space in which we will be able to take our qubits. And just for the formula of the error, instead of checking only like what we know this, just as we said earlier, like we try to have pure states, and so it's like we try to purify it with air. So not only can we just not just use like the formalism of a ket, we can write it a vector, but no, here we still use this because after the decoding and encoding, we still have this problem that like yes, at the beginning we have a pure state, but after the compressor, like encoding decoding, there is some errors, and when it goes into the kernel, there is like loss of information, some noise, and the mixed states, which is one who have some noise or some errors, cannot be just rated as a simple ket. So we need this to be rated as density matrices, and so we need also this to be rated density matrices to do literally the difference between both of them. To finish, like yeah, I go through alpha, but like maybe I can define you alpha, zeta, delta, and purification. Like alpha, as I said, it's just a compression rate, like it's number of qubits by message you can authorize yourself by after compression. Like you begin with n qubits, and the encoding kernel, we just reduce it, is a literally smaller space of alpha n. So we'll have like alpha n qubits in a way. So you go from 0 to 0, and yeah, you reduce to alpha n qubits instead to 2 of the power of n in a way, or more like. And delta is the tolerance of the protocol. So yeah, we would just want like at which point like we want it to be equal, but like little loss, not importance. For example, we don't care about the 1000 zeros in the if we have like to distinguish between 0 and 1, that I launch 1,000 times. And yeah, from the purification, just a good condition that we talk like where or encoding and decoding just act on system A, but the formula calculate like the global error about A error. So we further encoding and decoding to preserve the global state to be sure they will not destroy entanglement, and yeah, just check about it, and yeah, and the any purification works no matter what it's linked to it too. So basically, maybe to illustrate like better the compressions, like at the beginning you have n qubits, and after you have alpha n, but alpha should be like strictly superior to 0, but also strictly inferior to 1. So you know you have 0.5, you compress about it, and so after you 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 just work with it, like So it will be like a space of 2 of the power of n, and here like 2 to the power of 1 over 2 of n. So yeah, you just compression, from n qubits to alpha n qubits, with alpha being strictly inferior to n to compress.